In this video, I want to tell you about a problem in quantum mechanics that was left unsolved by Erwin Schrödinger and Werner Heisenberg. It remained an open problem for 85 years until in 2014, a couple of physicists by the name of Maccone and Pati found not one, but two satisfactory solutions. In order to understand just what this problem was, let's first go back to 1927 when Heisenberg initially formulated his famous uncertainty principle. In a paper titled The Physical Content of Quantum Kinematics and Mechanics, Heisenberg considered what level of precision is actually possible in various physics experiments. In particular, he analyzed how one could measure the position of an electron with a microscope. The precision of this type of measurement is only limited by the wavelength of light used. So, the smaller the wavelength, the more precise and accurate the measurement will be. However, as the wavelength gets smaller, something called the Compton effect begins to play a significant role. What the Compton effect says is that anytime a photon interacts with an electron, the electron will experience a recoil effect, which causes a change in its momentum. And the smaller the wavelength of the photon, the larger is this change in momentum. So Heisenberg reasoned that because of the Compton effect, the more precisely the position of an electron is known, the less precisely can the momentum be known. And thus he arrived at his uncertainty principle, which was originally written in this form. Now, Heisenberg's goal in his paper was to provide a qualitative understanding of quantum theory. So he based his arguments only on qualitative examples and experiments. The exact mathematical derivation of the uncertainty principle wasn't found until later that year when a physicist named Earl Kennard proved that when the position and momentum operators act on any normalized ket psi, the following inequality holds. This is just the standard version of the uncertainty principle, which you'll see in typical quantum mechanics courses and textbooks. Soon after, in 1929, a mathematical physicist named Howard Robertson was able to generalize this result to an uncertainty relation that holds for any self-adjoint linear operator or quantum observable. And the very next year, Schrödinger further improved it by proving an even stronger uncertainty relation. I already made a video all about how these uncertainty relations are related and how the first three are just specific cases of Schrödinger's. If you're interested, I put a link to it in the description section below, so be sure to go check it out after this. Okay, so what began as a qualitative argument in Heisenberg's original paper quickly developed into these two precise general mathematical uncertainty relations. And one of the strengths of each of these relations is that they are able to quantitatively express a fundamental concept in quantum mechanics. Namely, that it is impossible to prepare a state such that incompatible observables are both fully known. That is, when the commutator of two observables is non-zero, these relations can show that the uncertainty product of the observables is greater than or equal to some value. This is quite an achievement. So, where is the issue? What problem did these great physicists leave unsolved? Well, as incredibly powerful as both of these relations are, they each suffer from something that is called the triviality problem. And this can be seen from the following simple example. Let's suppose we had a system that was in an eigenstate of the observable A. Remember, this means that when A is applied to the ket psi, it will satisfy this equation. And let us further suppose that the observable B is incompatible with A. So the commutator of A and B is non-zero. Now, if we want to calculate the bounds that both of these relations give in this case, we get the following. So what happened here? Well, since we are in an eigenstate of A, delta A squared equals 0, and this forces the terms in each of the equations to vanish. So in this case, these relations provide no information. And since A and B are indeed incompatible here, this means that these two relations are unable to fully capture the notion of incompatibility. What is needed is a new formulation of an uncertainty relation that can give a meaningful inequality in all cases where the two observables are incompatible and only produce this trivial inequality for compatible observables. This is precisely the problem that was left unsolved by Schrödinger, Heisenberg, and others. In fact, for 85 years, no one was able to produce a satisfactory solution to it. However, in 2014, two physicists by the names of Lorenzo Maccone and Maccone-Pati were able to derive not just one, but two uncertainty relations that solved this problem. So, how did they do this? Well, their key insight can be best seen by visually interpreting the uncertainty relations. If you plot the uncertainties of two observables, A and B, so delta A squared is this, and delta B squared is this, then what these two uncertainty relations say is that the area of this square has a lower bound. It must always be greater than or equal to the values on the right-hand side of the inequality. And if the observables happen to be compatible, then the area is 0. However, since these relations suffer from the triviality problem, there will be certain cases where the area will go to 0 even when the two observables are incompatible. And it does this because the uncertainty of one of the observables goes to 0 in these cases. Maccone and Pati's key insight was to realize that if you use the sum of these uncertainties rather than the products, you could provide a much stronger bound. Now, instead of describing the area, you would be describing the length of the diagonal. And the advantage to this is that the length will only go to 0 if both delta A squared and delta B squared equals 0. In other words, it will only be 0 if A and B are compatible observables that can both be fully known. If A and B are incompatible, however, then the length of the diagonal is guaranteed to be greater than 0. Okay, so that was the key insight. But how did they go about proving a new relation? What is this sum of uncertainties actually bounded by? Well, as I mentioned earlier, they were actually able to prove two uncertainty relations, and the proofs were astonishingly simple. Now, although they were simple, they do require a fair amount of algebraic manipulation, so I will only give you a brief overview of their steps. I also provided a link to their paper that contains the full proof in the description section below, so be sure to check it out if you're interested. Surprisingly, each proof consists of just two main steps. For the first relation, the initial step was to define two new operators. The next step was then to apply the Cauchy-Schwarz inequality, which bounds inner products by the norms of each vector. And by simply doing some careful algebraic manipulation, this relation follows. For the second relation, they used the same new operators C and D, but this time they applied the parallelogram law to produce a different bound. And again, by doing some careful algebraic manipulation, this different relation follows. So from these very basic steps, they were able to prove two new, stronger uncertainty relations that entirely avoid the triviality problem. And although these relations might look quite complicated, they really just center around the commutator of A and B. You can see it explicitly in this term. And if you expand the other terms, you'll see that you just end up with modified commutation expressions between A and B. Now, this psi perpendicular term is just any state that is orthogonal to the original state psi. And this one also is orthogonal, but with some additional constraints, which they explain in detail in the paper. And so, by a simple shift from uncertainty products to uncertainty sums, Maccone and Pati were able to successfully capture the notion of incompatible observables that is so central to quantum mechanics.